Good morning everyone. Today we are going to see the topic aseptic equipment design. So before going into that today's lecture, I would like to remind you what all we have discussed in the previous lectures, which is nothing but fundamentals of aseptic processing. So these three lectures are interlinked to each other because without knowing the fundamental concept I cannot design a process. So without process requirements I cannot design a equipment. So whenever we discuss the equipment design, there may be a process parameters to be calculated, and the process design ultimately lead to the equipment design. Okay, so before going into this today's lecture, we just a recap what we have discussed yesterday. So we started with definition of aseptic processing and what are all the main components involved in the aseptic processing. So then we defined the temperature, and this is the main process. So which has the raw product supply tank, positive displacement pump, deaerator, and all these are heat exchanger, pre-cooler and final cooler. And we have a static mixture here. Today we are going to see what is the usage of that, and after that we have a aseptic surge tank as well. So then after that it goes for aseptic filling and packaging section, right. So after that we also seen the conditions for UHT, ultra high temperature processing. So that is nothing but 140 degrees centigrade for 4 seconds. The shelf life is 1 to 2 years, and what is the code of federal regulations for aseptic or UHT processing. And also I told you, or I have given you some home tasks to check after UHT processing. So what are all the nutrient values, and before the UHT processing in the raw milk, what are all the nutrient content values. So either we have compromised anything or not. And also we have discussed advantages and disadvantages of aseptic processing, and what are all the aseptic processed products, and what is the difference between conventional and aseptic processing, and what are all the source of heating medium used for latest methods of sterilization, right. So in this itself I have started discussing the equipment design. So what we have discussed yesterday is two equipment we have discussed yesterday. One is pumps. The pump section, so we have discussed for low pressure drop what should be used, for high pressure drop what should be used, and we mainly told aseptic processing is for only the pumpable fluids or the liquid which contains particulate solids. Pumpable fluids, either it may be of homogeneous liquid or the liquid may be containing some particulate matter. Liquid particulates, right. So when the liquid particulates are contained, so then viscosity comes into play. That is a parameter we need to look into. So based on that also low to medium viscosity, so what kind of pump I would be using, right. So all these three categories we have seen which pumps to be used. Then we also have seen about the heat exchangers. Though we have discussed the UHT processing earlier itself, maybe second lecture itself, we haven't got into detail about each heat exchanger types and pump type and all. So hereafter we would be seeing each equipment, what are all the constraints and how do I design that, right. But I think plate type heat exchanger we have designed in the sense how many number of plates required in each section. We have done one problem in pasteurization probably, right. So in the heat exchanger wise we have seen three categories. One is of tubular or shell and tube. Another one is plate type heat exchanger. So the other category is SSHEs, scrapped surface heat exchanger, right. So this is used for particulate solids, because it has the rotor tube, right, and in this the blades are attached. This blades are used to rotate, and also it takes care of the good mixing in the product side, right. When liquids containing particulate solids, then this is the most wanted one. So, other two normally homogeneous products, or we have also told if it is a 1/8 inch of particulate products are there in the liquid products, then that case also, that situation also this may be used, but your particulates of should be very small size when you have to use either tubular or plate type heat exchanger, right. And also here we have seen disadvantages and advantages. So, sometimes not only the product, we may look into some of other features as well. So, for that it might help you, and these are all indirect type. So, then if you go for direct type, then there is a two system, one is steam injection and steam infusion. So, these were direct heat exchanger, either steam is injected into the product or product is infused into the steam. So, based on that, for here also pros and cons we have seen, right. The next major item in the equipment design is your holding tube, right. So, the holding tube is designed to accomplish the lethality for the product. So, holding tube normally holds the product for certain, here it is, to at hold temperature and resident time combination for certain time and temperature to achieve the product lethality, right. So, the product sterility is assured at hold temperature, this temperature and the resident time. And one of the lectures also I mentioned you in the safety concern, this is very much important, because it is a sloped upwards at least 0.25 inch per foot to eliminate air packets and ensure self draining, because if there are any milk packets stays in the holding tube, so that also lead to further contamination. So, it should be sloped up as per the GMP good manufacturing practices, and smooth interior without protrusions, because there should not be any protrusions, because if you have a pit kind of thing, then here also your milk packet stays, and if not taken care in the cleaning, or if the same is used for the next batch, then there may be a chance of contamination. So, contamination happens through these protrusions, and easily disassembled for inspection. So, if you want to inspect, then it should be easily disassembled, and fail to safety system for reassembly, so that holding tube is not shortened or changed in the diameter. For example, when you reassembling, so you need to make sure that there is no change or shortening of the whole tube. So, for that there may be a mechanism, for example kind of lock mechanism, right. So, if I have a 6 part, so the first part only can fit into second part only can fit into third part, or third part can only fit into fourth part, right. So, that is a fail to safety system. So, if you leave anything, then you will not be able to reassemble it properly, right. So, that kind of mechanism should be there in the holding tube, and this would change the minimum residence time, because if the length is changed, then there may be a problem in the residence time. Residence time is nothing but the particle, how much time the particle spends inside the tube. So, that is nothing but minimum residence time. Any shortening length in the holding tube will reduce the minimum residence time, then you won't get the product sterility correctly. And condensate drip or draft of cold air which could affect the product temperature in the tube. So, in the tube there should not be any condensate drip or draft of cold air. The pressure in the whole tube must be maintained sufficiently above the vapor pressure, because if it is below, then there may be a flashing or boiling which happens in the holding tube. So, if that sensible heat of the product is used for flashing or boiling, then the product temperature automatically reduces within the holding tube. So, your product sterility will not be achieved, the temperature less than that of the commercial sterility temperature. The temperature of the product should be monitored, because from the holding tube it goes to cooling section. So, holding tube, it comes from the heating section. So, the both places the temperature should be monitored, both when it enters into the holding tube and leaves the holding tube, and temperature recorder controller is used. What is the purpose of this is, for example, here I measure the temperature, I connect it to the controller. If the temperature is less than that of the sterilized temperature, it will send back the product to the heating section itself. This we have discussed in the HTST processing. So, there it is done by the FDV, flow diversion valve. So, here it will be monitored by the recorder and controller. The product temperature measured at the exit of the holding tube is used to determine the adequacy of the process for commercial sterilization, measured at the end of the holding tube, right. So, this tells us whether the particular commercial sterilization is achieved or not. The next important equipment which we have seen for the aseptic processing is the deaerator. So, what is the function and need of deaerator? The air is removed to prevent undesirable oxidative reactions which occur as the product temperature is increased during the process. So, here in the aseptic processing, whatever we have seen, the deaerator kept in between the preheater and the final heater. However, the placing of deaerator comes from the product characteristics, right. Based on the product characteristics, I can keep wherever I want, because why we will discuss here. Here it is done to remove the oxygen, because the at high temperature, which is nothing but a sterilization temperature, oxidative reactions happen, so that it will lead to some off flavors in the product. So, due to that reason, deaerator is kept. The deaerator is a vessel in which the product is exposed to a vacuum on a continuous flow. So, this you might be knowing. The location of the deaerator is dictated by the product. Why? Because at high temperature the non-condensable gases are less soluble, but the flavor constituents are also more volatile, right. So, high temperature, if I do deaeration, then it will take care of the non-condensable gases, because they are less soluble, but at the same time the flavor constituents, whatever we have, vitamins and other flavor constituents, so those were highly volatile at high temperature. So, this is the optimization, right. Like I need to do it in high temperature, but that high temperature should not be of volatile temperature for the flavor constituents. So, more economical to operate the deaerator at high temperature if the product will tolerate it. So, it is based on the product. So, if I am able to manage my flavor constituents at that temperature, then I will be doing it at high temperature only, maybe after the final heater as well. The residual oxygen in the product becomes an even more important, since many of the packaging materials exhibit an oxygen permeability, even though small and not affecting asepsis, can lead to product quality deterioration over the storage time. So, one argument would be like I am also packing it with oxygen permeable packaging only. So, anyway that allows the oxygen. So, what is the big deal in doing it in the aseptic processing line itself, right. But however small we could reduce, that will greatly improve my product quality deterioration. So, that is the reason the deaerator is kept in the aseptic process line. So, then the next one is aseptic surge tank. So, the aseptic surge tanks are used in aseptic processing systems to allow the accumulation of sterile product period to packaging. So, normally when it comes out of the holding tube, so every day maybe I will be processing some 25,000 or 15,000 liter per hour, right. So, whether I will be able to package all the volume it is produced or not. So, based upon that, number of surge tanks or storage tanks would be designed. So, it is nothing but to between the product line, after the final cooler, after the holding tube, there is a cooling section here. So, after the cooling section, so it is introduced into the surge tank. So, here whether I will be able to pack all the volume produced here or not, based on that number of surge tanks would be designed. So, the ranging in capacity from about 100 gallons to several thousand gallons. The tanks provide flexibility, especially for the system in which flow rate of the sterile product is not compatible with the packaging capacity. This is what I told, right. So, I am producing 15,000 liter per hour, but only I will be able to handle less than that, then maybe of this size I will design the surge tank and keep the product, because the whole system is aseptic environment only. So, I can store the sterilized product after the cooling section. So, valving that connects the storage tank between the end of the cooling section and the packaging system allows the processor to carry out the processing and packaging functions more or less independently. So, this is what we told. So, I need not pack everything what is produced. So, if this surge tank helps me to store it, and according to my packaging capacity in the packaging lines, I would be using my sterilized product which is stored in the surge tanks. The product is pumped into the surge tank and is removed by maintaining a positive pressure in the tank with the sterile air or other sterile gas. That is the reason here the N2 or air. So, this already in a sterile environment. So, this is used for this purpose to maintain a positive pressure. So, the positive pressure must be monitored and controlled to protect the tank from contamination. Usually the back pressure valve mechanism would be helpful in this situation, right. So, the positive pressure must be monitored and controlled to protect the tank from contamination. There should not be any contamination. So, that will be taken care by the back pressure valve. Okay, so these are all the major equipments. Now we know how to design and what are all the design criteria I need to look into while designing a aseptic equipment system. So, the major ones are pumps, heat exchangers, either direct or indirect type. Then there comes a holding tube and there is a surge tank, and we have also seen static mixture that will be used to just mix the product. Why I will be telling in maybe a few slides after. So, what is the need and why the static mixture is kept, and also all are maintained in the sterile environment. So, now we are going to see how the product characteristics during thermal processes affects equipment design. So, why we are discussing here more specifically on product characteristics, I already told here in the aseptic processing. So, this is done in the continuous flow, right, and continuous flow it is done for liquids, and liquid contains particulates. So, it has all the phenomena. One is fluid flow phenomena and as well as heat transfer. In the heat transfer all the things would be coming, conduction and convection are major. So, that is the reason. So, each product characteristics will affect the process define obviously affect the sizing of the equipment, right. So, liquid or liquid plus particulates and size of the particulates yesterday we have told, right. So, in the liquid my particulates are there. So, when I heat it, the heat has to penetrate through the wall by conduction, then it has to be convected to the liquid. From the liquid it is again convected to the solid particle, and within the solid particle it is again the conduction. So, the geometric center of the solid particulate product in the liquid to be at sterilization temperature. That is what our aim is. So, in between these many resistances heat has to face before reaching the geometric center of the particle, and also we told the liquid particles may be of various sizes. So, in that case the bigger particle, because the bigger particle resistance would be more, in the bigger particle geometric center your sterilization temperature should be maintained. And product viscosity, obviously one is the liquid itself viscous, or the number of particles what you add also increase the viscosity of the total product. And thermal sensitivity of the product color and flavor. This is also important product characteristics. And quality changes include nutrient loss, that is nothing but enzyme destruction, flavor and color change, and coagulation of proteins. So, these also to be taken care doing thermal processing. So, this many a times we have discussed. So, my aim is not only killing the pathogenic or food spoilage microorganism, my aim is also to maintain the nutrient quality and nutrient color, and here one more is added is nothing but coagulation of protein. So, if it coagulates, then it automatically increase the viscosity of the product. And components can be aseptically added after cooling of the product prior to packaging. So, if you find it like okay 139 for 4 seconds is needed for UHT, and at that particular sterilizing temperature, if my product loses any nutrient, so that components can be added aseptically after cooling the product to compensate the any losses during the thermal process. So, this is also one of the way to maintain the nutrient content in the final UHT processed product. So, the next one is the temperature requirement for sterilization of low acid foods must exceed 121.1 degree, whereas the acid or acidified products, fruit juices and drinks could be sterilized at temperatures below 100. So, this we have already seen right in the pasteurization. So, I won't be I just look for 5D or 6D log reduction, as well as my the temperature for processing is below 100 only. And for the low acid food, these are prone to Clostridium botulinum. So, there I need to maintain 121.1 degree centigrade strictly. And also while designing the equipment, we told about one of the options, right. For low acid food, when you have a particulates in the liquid, so one way it can be handled is because the low acid foods are more prone to contamination. So, while processing in the aseptic processing line, so here the solid particles are sterilized separately and the liquid particles are sterilized separately, and then these both are mixed, and then the further operations are same, right. So, that is the way low acid food can be taken care in the aseptic processing line. So, the low acid food, this is the strict temperature regulation we need to follow. And the major thing is the pH. pH also affects the time temperature combination quite heavily. So, this comes under low acid food. So, this goes to acid food category. So, if you see acid food 90 degrees centigrade and 40 seconds is enough, but if it is a low acid food, this needs 140 degree for the same 40 seconds. The same thing for 20 minutes, it requires only 75 degree, but at the same time my low acid food requires 115 degree for 20 minutes. Okay. So, then from acid to low acid, the temperature requirement is increasing for the same time of the processing. And thermal conditions needed to produce commercial sterility in the product depend on nature of the food, which is nothing but a pH and water activity. So, this we have already told, greater than 4.6 and greater than 0.85 for low acid food, and storage conditions following the thermal process, whether you wanted to store it in refrigeration or in the room temperature itself, and heat resistance of the vegetative microorganisms or spores. So, this is the log reduction, and heat transfer to the food, it comes from the heat penetration test, and initial loading of the microorganism. This also we have seen that N0 is very much important. So, if it is normally it is practiced 12D process value, but if initial spores would be high, then we need to be worry about for that 12D process commercial sterilization. In SSHE, that is nothing but a scrapped surface heat exchanger. The tube is lined with a specific material to minimize the corrosion of the tube, because the tube is directly exposed to the product material sometimes foul the tubing. So, that can be taken care by using specific material coating in the surface of the tube. The material is usually specific for a given food group, since it is a food material and already our aim is to minimize the contamination. Which kind of coating material you use throughout the tube, we need to be very much careful about, and also it should be consistent with the food material. And sometimes what happens is this corrosion problem can be well taken care by the product itself, because certain product at certain temperature only will have the corrosion property. For example, at high temperature my corrosion would be very low. So, in that case then corrosion may not be of a problem in the heat exchanger, that may be a problem in the cooling section or holding tube, right. So, for that reason also we need to study the product characteristics, at what temperature corrosion rate is high. So, example is cheese sauce, milk, egg proteins. So, these foods causes the corrosion, but it is also a function of temperature. So, we are going to do one problem as a design example. So, here we were told to design a holding tube, right, holding tube of a UHT aseptic sterilizer for a homogeneous milk at 135 degree. Right, the homogeneous milk is heated to 100 degree through the regeneration. So, now you are very familiar with the terminologies, and heating section of the heat exchanger. So, regeneration and heating section heats at 100 degree. The milk is further heated by a steam injection. This is the direct heat exchanging system to 135, and it is maintained at the sterilization temperature for the required time, after which it is flashed to remove off flavors and then cooled in the regeneration and cooling section. This is whole UHT process they have explained. So, we supposed to design here holding tube for UHT aseptic sterilizer of a homogeneous milk at 135 degree centigrade. So, the main equipments what we have seen is pumps, heat exchangers, holding tube and aseptic surge tank, right. So, in that the heat exchanger design we have already seen in the pasteurization. So, how to calculate number of plates in the plate type heat exchanger, and here we are going to design a UHT holding tube. Also calculate heat losses in the holding tube. The data were given, the density of the milk is given, viscosity of the milk is given, mean velocity in the holding tube is given, wall thickness of the pipe is given 7 mm, heat transfer coefficient is given, ambient temperature and F value at 121 degree centigrade and Z value is given, and here wall thickness is given, and actually the mass flow rate should have been given. So, I am giving here, you can note it down. Mass flow rate is nothing but 1800 kg per hour, because either one of the things should have been given, right. So, either the diameter or mass flow rate. So, if it is 1800 kg per hour, then it is 1800 divided by 3600 to convert it into second. So, this may be of 0.5 kg per second. So, the mass flow rate, this is also given data, you note it down. Okay, so, we are going to do this problem. Okay. So, the mass flow rate is given, we all know mass flow rate is nothing but this dot is nothing but rate, it represents the rate, it is a density velocity into area, density velocity. So, this is area, right. What we have to know is the area, because I was given mass flow rate, I was given rho and I was also given UI. Suppose yes, mean velocity of the holding tube is given, right. The mass flow rate I just now calculated 0.5 divided by density of the milk is given. I think it is so much watery milk, because the water density itself given as 1000. So, 1000 into 0.5. So, it is nothing but 10 to the power of minus 3. So, from this pi d square upon 4 is nothing but 10 to the power of minus 3. From this I will calculate d as 0.035 meter. So, remember I already told, so when I use the numericals, these kind of adjustments I will do in the formula itself. So, there may be difference in the numerical values. For example, you would be getting 0.04 or 0.036, but remember the procedure but not the numerical values. You do it on your own way, and while doing assignments and question paper, so for that final exam, then I will take care of how many decimals you supposed to look for answer, or one way is do it and check for the nearby answer. For example, the options are given as 0.035 or 3.5. So, then you are getting around 0.043, right. So, there may be a problem because you have done one go, or you have done 1000 into 0.5 and get the value, then 0.5 divided by that value. So, these kind of adjustments may increase or decrease the final value what I have done. So, then look for the nearest answer. Okay. So, that you please keep in mind. So, do not look for the numerical values whether it is exact or not, right. And the next one what we supposed to calculate is, because what it was asked is length of the holding tube. Length of the holding tube is nothing but Ft into U max. So, this is nothing but a maximum velocity right. So, this Ft is in nothing but the residence time, right, the time required for holding tube, that is nothing but a process value here. So, the normal formula is nothing but the Ft is in minutes. So, the L is the length of the tube. So, this is in minute and U max is in nothing but meter per minute, right. So, you will get length in meters. So, this is nothing but a process value, and U max. U max I do not know as of now, but I know only average velocity, right. The formula which connects the average velocity and maximum velocity is based on the flow characteristics, whether it is a laminar flow or turbulent flow. Right. So, if it is a laminar flow, then your V average would be V max by 2. So, if it is a turbulent flow, then you will have the V max is nothing but 1.25 of average velocity, right, or you can write like average V max equal to 2 into V average, right. So, then we supposed to select here whether my flow is laminar or turbulent. The criteria is Reynolds number. So, then only I will be able to calculate my V max from the V average given. Then after that I will substitute in the Ft value to calculate L, which is nothing but a holding tube length. So, Reynolds number here is D rho V upon mu. So, D I have just calculated. So, which is nothing but 0.035 into 1000 into 0.5 divided by 0.3 into 10 to the power of minus 3. So, which comes around for me 60,000. So, obviously this is a turbulent flow, right. So, the RE is the measure. So, less than 2100 we call it as a laminar, 4100 above we call it as a turbulent. So, this number may be of changing. So, this is approximately I am telling. So, in between this there is a transition layer, transition region which happens from laminar to turbulent. Okay. So, since it is a 60,000, so obviously turbulent. So, I can calculate my maximum velocity by just multiplying 1.25. So, this I can use it as a U only, so that you will not get confused. U average, U max and U average, right. So, now my U max is nothing but 1.25 into 0.5, which is nothing but average velocity. So, which is nothing but 0.625. So, then I supposed to calculate Ft value, but Ft value at 121.1 is given, which is nothing but 4.5 minute. and Z is also given. So, yesterday we have done one problem. The basic formula goes like this: ln of f upon f naught, which is equivalent to T naught minus T upon Z. So, then f is nothing but f naught into 10 to the power of T naught minus T upon Z, right. So, for me what it is given is 121.1 is given, which is nothing but f naught 10 to the power of T naught minus 121 point, just let 121 only, 121 is given divided by Z value is given. So, this is given, but what I supposed to get is 135, right. Our temperature is 135. So, I supposed to get it 135 degree. So, which is nothing but f naught into 10 to the power of T naught minus 135 divided by 10. So, if you take it, if then 135 is nothing but f 121 into 10 to the power of 121, because this goes as a minus 135 upon 10. So, which comes around 4.5. So, your f 121 value, and this particular value comes around 0.04, which is nothing but 0.18 minute. So, or otherwise I can say f at 135 is nothing but 10.7 second. So, I have calculated my ft, I have calculated my umax. So, the length of the holding tube is nothing but ft into umax. So, which is nothing but 10.7 into 0.625, which comes around 6.7 meters. Okay. So, then anything else is asked? Yes. Also calculate the heat losses in the holding tube. So, heat losses in the sense, so I have a holding tube here in the aseptic processing. So, this is exposed to the aseptic environment. So, that means air, right. So, there would be a convection losses. So, due to losses, how much temperature reduction is there in the holding tube, that we supposed to find it out. And certain assumptions we need to make here. So, assumptions in the sense, so the whatever the product temperature, so that is the outside temperature, right. So, the I mean outer wall temperature of the holding tube is also 135 degree centigrade. And one more thing is, there is no fouling resistance, because I am not going to calculate the overall heat transfer coefficient. Fouling resistance in the sense, when the heat is conducted from the product to tube wall of the heat exchanger, there is no fouling factor. So, because of which there is no heat resistance. So, that is why we told the product is at the outer wall, the temperature is nothing but 135 degree itself. And one more thing is, I need to calculate outer dia. I am given the thickness. So, I calculated 0. What is the inner dia? Yeah, 0.035 plus 2 into 7 into 10 to the power of minus 3. So, it comes around 0.05 meter. So, then I supposed to find out what is the area. So, area is nothing but pi d L. So, pi into d is d we found out, outer dia, into L we just found out, that is 6.7. So, approximately it is coming around 1 meter square. So, I know area, then I can calculate heat loss due to convection. So, which is nothing but Q is equal to HA del T. So, H is given 9.8, A we found out 1, and del T is nothing but the ambient temperature is given, right. Yes, ambient temperature is given as 20. So, the product temperature is 135. So, 135 minus 20, that is nothing but 115. So, which comes around 1127 watt. right. So, another heat loss due to convection only, then we have assumed there is no radiation loss, loss is negligible. But it is also very low temperature, 135 you will not get any, the assumption is valid assumption only. Okay, so I have calculated the heat loss. So, from the heat loss I will be able to find out what is the del T required, the MCP del T. The specific heat of the product is given, no, you can take it. So, it is a homogenized milk, if you remember the pasteurization. So, we have taken I think 3.8 kilojoules per kg Kelvin. Alright. So, we substitute here the mass flow rate is Q we found out. So, from this del T is nothing but Q upon m dot Cp. So, Q is nothing but 1127, mass flow rate is 0.5 and Cp is nothing but 3800 because it is in watt, watt is nothing but joules per second. So, you would be getting around 0.6 degree centigrade. So, what happens, you are having a holding tube, right. So, the product is at 135 degree centigrade and length of the holding tube we just found out as 6.7 meter and it is in the sterile air environment which is nothing but a 20 degree, though the insulation is proper, there may be a heat losses due to convection. Due to that, then it is losing almost 0.6 degree temperature decrement in the product. So, one way we could avoid it is, so when it comes out of the final heater itself, so instead of the requirement of 135, I will be heating it to 135.6 degree centigrade, so that the product is always maintained at 135 degree, because the 0.6 degree del T difference is there in the holding tube as per the data given, and also we have assumed there is no fouling resistance and there is no radiation losses, how much ever is negligible. Okay, so this is the way I design the holding tube as well as I adjust the product formulations according to the needs. So, this everything comes from the fluid flow and heat transfer, right, because I need to understand here what should be my flow characteristics. Based on the flow characteristics only I can fix the maximum velocity of the product here. And one more thing here also, directly the H is given, otherwise for the turbulent heat transfer there is a correlation which comes as a function of del T and D. So, for this the H would be 1.42 because it is a turbulent flow heat transfer, del T upon D power 0.25, this D is nothing but a outer dia of the pipe. So, del T is nothing but temperature difference between that is nothing but 135 minus 20, and this is based on the turbulent flow characteristics and specific for the range of non-dimensional parameters. So, these kind of correlations I would use and calculate the heat transfer coefficient and substitute here. So, everything comes from the fluid flow characteristics and product characteristics as well as heat transfer characteristics of the product. So, this I have shown you as a example problem how to design a holding tube, and we have already discussed how to calculate the number of plates in the plate type heat exchanger. So, I will end this lecture with this, then we will see about the aseptic process design in next lecture. Thank you.